What I'm going to do now is I'm going to unpack this model that we just fit in BRM, and I'm going to study some of the properties of the model that we are trying to use to understand the data that we are looking at. Okay? And the two important ideas I want to get across in this lecture and in the coming lecture is the idea of a prior predictive distribution and the idea of a posterior predictive distribution. Right? So let's revisit what the model looks like. So unlike a linear model, in a linear model, the full specification of the model would be equation 2. But in a Bayesian model, when I say model, I'm talking not only about the generative process for the observed data, I'm also including my prior specification for the parameters. So the model, when I say the model in Bayesian data analysis, I'm talking about equations 1 and 2 taken together as one statement about the model. Okay, so that's a big difference between the frequentist and the Bayesian approach. Now, having specified some priors on the mu and sigma parameters, even before I've seen any data, I can already generate simulated data from this model, right? So intuitively, if I just take a sample from a uniform and I take a sample from this uniform distribution, I get a sample of mu and sigma. I could plug those in here and I could get a generated data point, right? This generated data point is called a prior predictive distribution. The formal statement is here. All I'm doing is I'm integrating out the theta parameters. I discussed this last time, what integrating out a parameter means, right? So, but that's all I'm doing here, and it really doesn't matter how many parameters I have. I can do this. In this case, I have 2. I could have hundreds, right? I could still generate a prior predictive distribution. So how does this work, right? How do I generate a prior predictive distribution? As I pointed out, I take a sample. This is just a toy version, okay? I take a sample from the prior for mu. I take a sample from the prior for sigma, right? I've got a number here and a number here taken from the prior distributions, and I plug those into the R norm function. So now you see the advantage of knowing the DPQR family of functions, right? We can use that to generate prior predictive distributions. So in this case, I'm generating five data points with this particular mu and sigma. So I get one predicted data set now, right? Before I've seen any data. I'm just studying the properties of the model given the priors and the generative process that is the likelihood function, right? So this is some simulated data. Now I can do this as many times as I like. So I could get multiple data sets of whatever sample size I want, right? And so in the textbook you will see the code for generating this kind of data, but I'm just showing you the output, of that kind of generative process. So what I've shown you is 4 simulated data sets, right? From the model that we have just specified. And just look at it, right? What do you see from this? The model is completely unreasonable because it's assuming, in this particular case, it generated data with a mean of around 9,000 milliseconds. So 9 seconds is the average reaction time for button pressing. Just imagine that, right? How realistic is that as a model? It's not, right? I wouldn't take 9 seconds to press buttons if I'm asked to just keep repeatedly pressing them, right? Similarly, this one is even slower, and this one is a bit more realistic, but still kind of strange here, right? So you see these weird distributions, and of course I didn't do the binning properly. That's why you see this single vertical bar here, and here. If I had binned it properly, you would see that they're kind of spread out around this very large value. But the main point I want to get across here is that these are unrealistic data points generated by the model. And what that tells us is that the priors are not reasonable here, right? I will show you later that they're not harmful if you're actually doing the data analysis, but as a model, this is not a very sensible model to assume for reaction times, okay? So now the question is, if the priors are not reasonable, the priors that I just specified, if they are not reasonable, what is my alternative, right? So that's an idea that I will unpack for you. And this falls out of this prior predictive distribution idea, right? If you look at the prior predictive distributions, you realize that the model is producing completely ridiculous data, then the first question you should ask yourself is, how should I change my model such that the priors are more reasonable, such that they produce more reasonable data, given the problem I'm working on, okay? And so in the Bayesian literature, there's a vast terminology, you know, for different types of priors. So in our book, we had to choose, you know, some classification. So we just chose this arbitrary, well, it's not arbitrary, but we chose this for our own book. So we have 4 basic classes of priors, and these are of course a continuum. So they are not discrete categories, but these are a continuum which kind of summarize the type of priors that one can, you know, use. So one type would be the type that I showed you already, a flat uninformative prior, right? This could be the uniform prior, and here I've got a uniform prior going from a very like from a negative value to a positive value. Of course, a negative value is not reasonable in this case, in this particular case, but in principle you could actually specify such priors. Okay. The second class of prior that we will use in the examples that I will show is something called a regularizing prior, right? So in this case, this plus sign that you're seeing underneath the normal here, after the normal here, what this is saying is that we are going to define a normal distribution prior with mean 0 and standard deviation 1000 in the usual way, right? But we're going to truncate it at 0. So what this model actually looks like, right, graphically, the actual shape of this model will be something like this. Right, this is the 0 point. So I would define a prior which has a particular mean 0 and some standard deviation, but I truncated at this point. So that means this part of the distribution is now gone. So the reason I'm going to use a prior like this would be if I want to stipulate that mu cannot be negative, right? If I'm talking about reaction times, you can't have negative 5 milliseconds reaction time, right? 0 is a lower bound. So this would be a reasonable way to truncate the normal distribution. So this is a truncated normal. Similarly, I could decide on a different type of prior, which we are calling principal prior. So what this is doing is that notice that the mean is no longer 0, but 250. The reason we call it a principal prior is that we know from previous research that button pressing or even intuition would help us here, right? That button pressing like this would not take more than 200 or 250 milliseconds on average, right? So you could assume that the prior is about 250 milliseconds, and you could put a pretty vague, you could allow for a lot of variation around that 250 milliseconds by defining a pretty large standard deviation here. So it's a principal prior because it centers the prior at 250, which is a reasonable prior assumption about reaction times, but it's very liberal about allowing the mu parameter to vary plus or minus 200 milliseconds, right? So it could be as small as 50 milliseconds or as large as 450 milliseconds, right? So that's what this prior is doing. And notice that I truncate this one as well. So it can never be negative, which is also reasonable here, right? And another class of prior that we will use a lot, especially if we do hypothesis testing with Bayes factors, a topic that I won't discuss in this course, but it's in the textbook. There, using informative priors is extremely important, right? So you should put in as much information as you can given the data that you've already seen in the literature or through meta-analyses or something. So there what I've done is, in this example, I've got a truncated prior with mean 200 and standard deviation 20, right? It's a much tighter prior. And in practice, when I actually write papers and do research, I generally use informative priors when I can. So if there's 20 years of research on a particular topic, I can do a meta-analysis, figure out the posterior distribution from the previous work on the particular parameter, you know, that people are looking at, and I can plug that into my model. So I'm building on prior knowledge, you know, to do my new analysis. So this is a very useful way to understand your data in the light of prior knowledge, right? So these types of priors can help you figure out what the data are going to tell you under different assumptions, right? So that's called a sensitivity analysis, using a range of different priors to understand how the posteriors change, or if they even change as a result of the change in the priors. So as I mentioned, there's no standard terminology. This is just ours. So you'll see different phrases or different terms used in different textbooks, but from the context, it'll be clear what type of prior is meant. Okay. So then in the next lecture, I'm going to give you an example of how one could do a sensitivity analysis to establish whether you have a more reasonable model or not. So you can use different priors to work out, which prior to choose for your final published analysis. That's coming up next.